Chapter 1 talks about chemical and physical changes. A physical change is when a piece of metal changes, but it does not change its chemical composition, such as turning ice into water and water boiling and tearing a piece of paper. While a chemical change is a change that occurs in a piece of metal and it changes its chemical composition, such as paper being lit on fire. It's something that you cannot get back. Chapter 2 talks about Dalton's atomic theory. Dalton's atomic theory begins with 4 postulates. The first postulate is all matter is made up of atoms. Atoms are indivisible and indestructible. Dalton's second postulate is that all atoms of a given element are identical in mass and properties. Dalton's third postulate is compounds are formed by a combination of 2 or more different kinds of atoms. And Dalton's fourth postulate is a chemical reaction is a rearrangement of atoms.
One of the topics Chapter 3 talks about is balancing equations. Having a balanced equation is important because then you know exactly how many atoms you need to form a complete reaction. To figure out if an equation like this one is balanced or unbalanced, first you need to figure out how many atoms per element you have on each side of the reaction. Because the h's aren't the same, you then have to balance the equation. And to do this, you can add coefficients right in front of each of these in order to balance it out. So for this example, in order to balance it out, you need a 4 in front of the ammonia, a 5 in front of the O2, a 4 in front of the nitrogen monoxide, and a 6 in front of the water. Now, when you multiply the coefficients out by the subscripts, you then figure out how many are on each side. So now you can see that each of these sides are balanced, meaning that the equation is balanced. Chapter 4 discusses different types of reactions, including an acid-base reaction, in which an acid and a base react together to become neutral. Acid-base reactions can either happen between a strong acid and a strong base, or a strong base and a weak acid. An example of an acid-base reaction is baking soda reacting with vinegar. So in this example, the baking soda is a weak base and the vinegar is a weak acid, and when they do react, they neutralize each other. So that's the reaction between baking soda and vinegar.
The main focus of Chapter 5 is the concept of gas laws. There are 4 main gas laws: Boyle's law, Charles' law, the ideal law, and Avogadro's law. Boyle's law is represented by the equation P1V1 equals P2V2, which shows that pressure and volume are inversely related. Avogadro's law is is represented as V1 over N1 equals V2 over N2, and shows that equal volumes of the same gas have an equal number of molecules and moles. The ideal law is represented as PV equals nRT. Lastly, there is Charles' law, which is represented by V1 over T1 equals V2 over T2. This law proves that the volume of gases are directly proportional to temperature. Because of this, we can show Charles' law in action by looking at a full balloon that was put in boiling water. The high temperature causes the pressure of the air inside the balloon to rise, causing the balloon to inflate more. The balloon deflates back to its original size once the temperature drops to room temperature. Chapter 6 focuses on energy transfers such as potential and kinetic energy. Potential and kinetic energy combine to form the internal energy of a system. Potential energy is the energy stored in an object, while kinetic energy is the energy of motion. These energies can be shown by a game of pool. Before it is hit, the cue ball has potential energy. Once the cue hits the ball, that potential energy is converted into kinetic energy. Then the cue ball hits the rest of the balls and transfers its kinetic energy to them. The total energy of all the balls that were hit is equal to the kinetic energy of the cue ball when it was first hit by the pool cue.
In Chapter 7, we focus on quantum theory and atomic structure. However, before delving too deep into the aforementioned concepts, one must first understand the nature of light itself. Light, one of the many forms of electromagnetic radiation, is made up of magnetic and electric fields that behave much like waves. The book stresses three important properties when studying the wave-like nature of light. Frequency is the number of fully completed cycles or periods of the electromagnetic radiation per second. The most common unit of measurement for this is hertz. A wave with a high frequency looks something like this, while a wave with a low frequency looks something like this, with this being the baseline for both. The wavelength is the distance between one crest and the next crest, or the trough to the next. The differences between the two look something like this. So from here to here is going to be our wavelength, or we can also do from here to here. Finally, the amplitude of a wave is the height of the crest or the depth of the trough from the midline. Waves with a high amplitude are vertically longer than those with a shorter frequency. So, if we did something like this, from here to here would be the amplitude, or we could also do from here to here. By integrating all of these concepts into one, you are then able to build off of these ideas and begin to understand the energy of waves, the various types of electromagnetic radiation, and how visible light works. Alright, so Chapter 8 deals with electron configuration and chemical periodicity. Throughout this chapter, we learn about the relevance of electron periodic trends and their exceptions. Starting with periodic trends, we have the trend in atomic size or radius. This trend decreases as you move to the right and top of the periodic table due to the effective nuclear charge, making those elements to the right of the table have more condensed electrons than their protons pull them closer. The second periodic trend is the first ionization energy trend. Ionization energy is defined as the amount of energy that is required to remove the outermost electron from a neutral atom. Ionization energy decreases as you move down the groups and as you move across the periods, because as you move across the periodic table, the atoms are smaller and the electrons have more closely bonded to their nucleus, making it more difficult to remove them. The third periodic trend is electron affinity, which is defined as the energy released when an electron is added to a neutral atom. Electron affinity increases from left to right and from bottom to top, with exceptions being the first period nonmetals and specific electron configurations.
Now it's time for Chapter 10.
The first topic for Chapter 10 is Lewis dot structures. Lewis dot structures are a really simple way to view molecules and the atoms and electrons that surround them. They were introduced in 1916 by this gentleman, Gilbert N. Lewis, and it's because of him that we can view these things so easily. Thanks, Gil. But how do we explain this? Easy. All we have to do is draw them out.
There's three basic parts to making a Lewis structure. Our atoms are represented by periodic table symbols. Example, C, for carbon. Our bonded pairs are represented by straight lines, And our electron pairs are represented by dots. For our example, let's draw out the nitrate ion, NO3 negative. First, let's figure out our total valence electrons. Looking at a periodic table, we see that nitrogen has 5, oxygen has 6, and we have 3 of them, and that negative sign counts for 1. Total of 24. So now let's draw out the basic skeleton. The least electronegative will go in the middle. And then we're going to distribute oxygen around it. Now, we're going to count each of these bonds as 2. 2, 4, 6, and subtract this from 24. This will give us 18, and that gives us the electron to distribute to everything else. 6, 12, 18. So we can see that each of these has their octet filled, but now nitrogen doesn't, and we don't have any electrons left. So what do? Easy. Let's just take off a pair from oxygen and represent it as a double bond. Now both are filled, because these all have 8, each of these count as 2 on the ends, and nitrogen does as well, because each of these count as 2. So this is it, but we have a negative charge right here. So when you have a charge, just bracket the whole thing and put that charge right there. That's the basic way to do a Lewis structure.
Now let's talk about the VSEPR theory. VSEPR stands for valence shell electron pair repulsion, and the theory basically says that to keep repulsion between electrons at a minimum, electrons around a central atom should be located as far away as possible. This results in some various three-dimensional shapes which we have different names for. Let's use the nitrate molecule we made as an example.
Geometrical molecular shapes depend on the number of bonded pairs and lone pairs. When you're dealing with bonded pairs, they only count as 1 for molecular geometry no matter what the type. Even though we have double here, it counts as 1 for a total of 3. No lone pairs because each of these is a full octet. You have to look on a list to be sure what matches with what. So in this case, this corresponds to the shape of trigonal planar. It looks something like this.
In these pictures, I've assembled a few more geometrical shapes. Quite a few are exactly as they appear and pertain to basic 3D shapes like pyramids and tetrahedrons. In these basic models, the bigger styrofoam balls are bonded pairs and the small ones lone pairs. Each also has a specific bond angle found by dividing the number of domains, which are specific to each shape, by 360. In this octahedral model, all of the styrofoam should represent bonded pairs.
Okay, so valence bond theory. Valence bond theory is that a covalent bond forms when orbitals of 2 atoms or molecules overlap and a pair of electrons occupy the overlapped region. Pretty boring, huh? Just hearing it like that? Well, how about this? How about I show y'all what this really is? Here we have 2 H molecules. They're floating through space all lonely. And because they only have 1 electron in their 1s orbital, they're trying to find each other to have a full shell. So, they're going to come together and find each other. And then when they finally meet together, they're going to merge. And then we have an H2 molecule. And they're happy, as you can see. Because the H molecule is one of the first elements on the periodic table, it's only going to have 1 electron to fill up its s orbital. And that means it's going to be unstable, so it's going to want to find another element or molecule to fill up its shell, just like another hydrogen molecule, H2. And that's going to make a complete1s orbital. So here we have the fluorine molecule, which has a full 1s, 2s orbital, and its 2p orbital is all full except for the last slot. So therefore, the H molecule, which only has 1 electron, would be perfect to occupy the last spot for it. So that's why the H molecule bonded away from the H2 and formed hydrogen fluoride molecule, because it has a full shell now. The 1s, 2s, 2p, and it's complete. And the reason the H molecule is separated from the H2 is because it's all molecules their end goal is to become more stable, which happens because after each orbital, it gains more stability. So by filling up its 2p orbital, HF is now more stable than the H2 molecule, which is only 1s orbital.